Imagine it's a quiet morning. Sunlight spills through your window, dust floating lazily in the air. Everything feels calm, simple, balanced. But here's the strange part. Even this familiar scene is a kind of illusion. Your eyes are only showing you a tiny slice of what's really happening. All around you, the universe is screaming with signals you can't see. Invisible colors of light, radio waves, X-rays, particles, and ripples in space-time, all passing through your body, right now, without you ever noticing. Among them is something especially weird. At this very moment, trillions of ghost-like particles called neutrinos are streaming through you every second. They pass through walls, through mountains, through the entire Earth, like it's not even there. They leave almost no trace. And yet some of the world's most powerful experiments and smartest physicists are obsessed with them. Why? Because there's a puzzle at the heart of reality. If the universe started in perfect balance, matter and antimatter created in equal amounts, then almost everything should have annihilated into pure light. No stars, no planets, no you. And yet, here we are. What if neutrinos never disappeared at all? What if they've been quietly recording the very first moment the universe slipped out of balance and decided to let matter, and our entire story, exist? So, as you sit there, in that quiet room lit by an ordinary star, it is worth noticing how much of what shapes your life never shows up in your field of view at all. Your eyes are tuned to one narrow band of colors, reds and blues and greens that you can name. Everything you call seeing lives inside that thin slice of the electromagnetic spectrum. Outside it, reality does not stop. It just stops being visible to you. Radio waves from distant stations slide through walls. Wi-Fi signals weave through furniture. Infrared light carries the warmth of objects. Ultraviolet light burns skin and shapes biology. X-rays pass through flesh and are stopped by bone. All of this forms a kind of weather made of light. And almost none of it is something you can sense without help. For most of human history, this extra weather might as well not have existed. People navigated by the colors of the sky and the changing brightness of the Sunday. Only when we started building instruments that could listen beyond what our eyes could do did the rest of the spectrum begin to appear as something real, not imagined. Take a very specific example. In the early years of the 21st century, an old Boeing jumbo jet was gutted and transformed into something strange. Instead of rows of seats and meal carts, its interior held mirrors, detectors, and control consoles. The aircraft was turned into an airborne observatory for infrared light, a joint project between a space agency and an aviation authority. It flew at altitudes of around 12 to 13 kilometers, high enough that most of the water vapor in the atmosphere lay below it. Water vapor is very effective at absorbing infrared light. From the ground, much of that part of the spectrum is blocked. But when you lift a telescope above most of the water, the sky changes. New structures appear in star-forming regions. Dust clouds that look opaque in visible light become almost transparent. The plane was called an observatory for airborne infrared astronomy. It began regular operations around the year 2010. Nothing about the stars themselves changed in that moment. Only the environment of observation did. The same galaxy, the same nebula, the same star-forming region. But shift the instrument slightly higher, and suddenly a different layer of truth becomes accessible. This is one of the quiet lessons of modern astronomy. You do not always need a bigger mirror. Sometimes, you just need to move the mirror to a different place. Change the medium between you and the universe, and you discover that what you thought was an empty patch of sky is not empty at all. The idea runs deeper than telescopes. Even the nearest and most familiar source of light, the sun, is already edited before it reaches you. From the surface of Earth, the sun usually looks yellowish or orange, especially near the horizon. It has become an icon in that color. Children draw it that way almost automatically. But if you were to drift outside the atmosphere and look at the sun from space, it would not be a golden disk. Its light, taken as a whole, is closer to white. The spectrum of that light peaks not in the yellow, but slightly toward the green and blue. The warm tint you see from the ground is the result of scattering in the air. Molecules in the atmosphere preferentially scatter shorter wavelengths. The direct beam you receive is what remains after that filtering. In other words, even before your eyes and brain interpret anything, the planet has already performed its own edit on the raw signal. So the thing that feels most obvious, the color of daylight, is already a compromise between what the star emits and what your environment allows through. The image in your mind is not a direct map of reality. It is a processed version, a convenient one, a useful one, but still an edited one. Now stretch that idea outward. When you see those striking images of galaxies and nebulae online, you are looking at another layer of editing. Astronomers combine exposures at different wavelengths, assign colors to bands of light that human eyes cannot normally see, and enhance contrast to bring out faint structures. None of this is dishonest. It is a way of translating information into a form that your visual system can handle. But it means that every glorious picture is, again, only one of many possible stories told about the same object. Behind each of those pictures, there are other channels that do not produce anything resembling an image at all. There are ripples in space-time detected as gravitational waves, subtle stretches and squeezes recorded by kilometer-scale interferometers. There is a background of microwave photons left over from the early universe, arriving from every direction with almost uniform temperature and tiny fluctuations. There are high-energy particles from cosmic rays slamming into the upper atmosphere. And there is a constant rain of neutrinos, which for now, we still mostly treat as a background rather than a view. From our position, we stand in front of an enormous wall of signals. Some we can convert into colors and pictures. Some we can only express as graphs and numbers. Some remain almost entirely silent, and yet we know they are there from their indirect effects. Our cosmos, as we experience it, is one particular projection of a much richer structure. You can feel that contrast even in ordinary life. Imagine a person lying still inside a hospital scanner. The room is chilled and controlled. Lights are soft. From the patient's point of view, nothing dramatic happens. They do not feel beams passing through them. They do not sense particles being created and destroyed. But in a positron emission tomography scan, tiny amounts of radioactive tracer inside the body emit positrons. Each positron finds an electron, annihilates with it, and the pair disappears into two gamma-ray photons flying off in almost opposite directions. Detectors ring the body and register those photons. Sophisticated software reconstructs where each annihilation likely occurred, building a three-dimensional map of metabolism and blood flow. Inside the patient, matter and antimatter are meeting and turning into light. Outside, a machine translates those silent events into an image. Between the two views, the person feels nothing special. They are the same organism they were earlier. The universe has just revealed one more layer of structure that was always there, now made explicit by a device tuned to a very specific kind of signal. If light alone can mislead or limit us this much, it raises an obvious but uncomfortable question. How much more is hidden inside phenomena that do not rely on light at all, that do not interact with electric charge, that cross our instruments almost untouched? What parts of reality never become images in any sense, not even false color ones, unless we build detectors with a completely different philosophy? Cosmology today is, in some sense, the accumulation of ways to work around our blindness. Each new kind of detector is a small rebellion against the idea that what we see is all there is. Gravitational wave observatories refuse to accept that only light carries information about violent events in distant galaxies. Radio telescopes refuse to accept that visible starlight tells the full story of gas and magnetic fields. Neutrino experiments refuse to accept that only charged particles are worth chasing. And yet, for all our instruments, there is still a feeling that we are tracing outlines rather than touching the core. The big questions about why matter exists, why there is something instead of a uniform bath of radiation, are not settled by sharp pictures. They are hidden in slight imbalances, rare interactions, and ghostly particles that almost never leave a mark. This is where neutrinos begin to matter for the story. They are not another color of light. They are not photons at a different energy. They are particles with no electric charge, moving through planets as if through fog, almost never colliding, barely responding to anything except the weakest of the fundamental forces and the slow pull of gravity. They carry information precisely because they ignore most of the universe. If ordinary light is like paint that sticks easily to surfaces, neutrinos are more like dry wind slipping through cracks. They do not build up. They do not linger. They pass through dense matter that would stop almost any other signal. And because of that, they can escape regions that light cannot. Stellar cores. The interior of collapsing stars, the thick plasma of the early universe. From our perspective, they belong to the next layer of invisibility. Not just unseen, but almost uninteractable. Not just beyond color, but beyond the whole logic of vision. That makes them frustrating to study. It also makes them uniquely capable of carrying secrets that nothing else can transport intact. When you walk through sunlight, you are bathed in photons that have bounced and scattered many times before reaching you. When you stand there, you are also crossed by neutrinos that have traveled huge distances almost without touching anything at all. If we want to know what the universe was like before it became transparent to light, before photons could move freely, we cannot rely only on the familiar tools of astronomy. We have to learn to listen to the particles that never cared about visibility in the first place. We have to follow the tracks of these almost non-existent messengers that drift through you every moment, without waiting for you to notice. To even begin, you have to accept that most of what is happening to you right now leaves no mark on your senses at all. Neutrinos are part of that silent majority. In the language of physics, they are fundamental particles. They are extremely light, so light that for a long time it was reasonable to treat their mass as exactly zero. They carry no electric charge. They do not respond to electric or magnetic fields in any noticeable way. They do not take part in the strong nuclear force that glues nuclei together. They only really participate in two interactions: the weak nuclear force and gravity. And gravity, at their tiny mass, matters almost not at all. In the usual list of forces, there are 4 entries. Gravity, which shapes planets and galaxies. Electromagnetism, which governs light and chemistry and all the familiar technology around you. The strong force, which binds protons and neutrons inside atomic nuclei. And the weak force, which allows certain particles to transform into others and is responsible for radioactive beta decay. Neutrinos more or less ignore the first 3 in daily life and mostly listen only to the weak one. That choice makes them almost transparent to the rest of the universe. This is why your ordinary detectors do not notice them. Most measuring devices are built around charge and light. Wires that pick up electric currents. Photodiodes that count photons. Scintillators that convert charged particle tracks into flashes. But neutrinos are neutral. They do not normally leave electric trails. They pass through mirrors and lenses without care. If they interact at all, they do so rarely and quietly through the weak force in a way that is easy to miss unless you prepare a huge mass of material and watch it for a long time. Yet in terms of sheer quantity, they are everywhere. The core of the Sun is constantly fusing hydrogen into helium. Each of those fusion chains produces neutrinos along the way. By the time that flux reaches the orbit of Earth, it amounts to roughly tens of billions of neutrinos, passing through every square centimeter of a surface, facing the Sun each second. Your body, if you think of it as an area and not as a person, intercepts that stream. Multiply that flux by the size of a human, and you end up with a number that is hard to intuit. Around 100 trillion solar neutrinos, give or take, pass through your body every second. They come from below as well as above, because the ones arriving from the far side of the planet have already traversed the entire Earth to get to you. They do not knock atoms out of place. They do not warm your skin. Almost all of them move on as if you were not there. If you could somehow freeze time and light up only the neutrinos, your body would look less like a solid object and more like a faintly defined absence in a vast river of passing points. Most of those points would be coming straight from the sunday. Others would be born in the atmosphere when cosmic rays hit air molecules. A smaller share would be relics from nuclear reactors, from distant supernovae, from the Big Bang itself. But altogether, they form an invisible current that flows through you without asking permission. Neutrinos are often called ghost particles, but that phrase can be misleading. They are not insubstantial in the sense of fiction. They are real excitations of fields, as solid in the mathematics as electrons or quarks. What makes them ghost-like is not that they are vague, but that they refuse to interact. Where a charged particle plows through matter, leaving ionization and light behind, a neutrino will usually slide between nuclei without doing anything at all. The scale of that refusal is hard to feel. So physicists resort to thought experiments in dense materials. Imagine a slab of lead, a metal much denser than water or rock, not just a shield a few centimeters thick like the one in a laboratory, something vast. A block whose thickness is roughly the distance from Earth to the sunday. Take a beam of typical solar neutrinos and send it into that block. You might expect that such a journey would guarantee many collisions. Yet calculations show that even after traveling through that entire 1 astronomical unit of solid lead, most neutrinos would still have failed to interact. Now stretch the thought further. Consider a thickness of lead not only as big as the Earth-Sun distance, but as extended as a full light year. That is the distance light covers in 1 year of travel in vacuum. For many kinds of neutrinos, their mean free path in such dense material is on that order. In other words, a neutrino can typically move through roughly a light year of lead before having a significant chance to collide with a single nucleus. You could surround yourself with an almost unimaginable wall of shielding, and still, half of these particles would walk through untouched. At the same time, on the scale of the whole universe, neutrinos are not rare at all. They are, by count, second only to photons as the most abundant known particle species in existence. The space between galaxies is filled with a thin sea of them. The inside of stars is flooded with them. The early universe produced a background of relic neutrinos that has been cooling and stretching along with space itself for almost the entire cosmic history. So we are in a strange situation. The particles that are in some sense the most common are also the ones we almost never see directly. They fill the cosmos like a gas of witnesses who refuse to testify unless asked the right question in exactly the right way. The invisibility of neutrinos is not just an external fact. It is also internal. Your own body is not only a target, it is a source. Naturally occurring radioactive isotopes such as potassium and carbon inside you undergo beta decay. In these decays, a neutron inside a nucleus can transform into a proton, emitting an electron and an antineutrino, or a proton can transform into a neutron, emitting a positron and a neutrino. These processes are happening quietly in your tissues all the time. Each event changes a nucleus, releases a small amount of energy, and adds another neutrino or antineutrino to the general flow. You do not feel those transformations. They are not a symptom of illness or a sign of anything out of balance. They are simply what matter does under the rules it has been given. From one point of view, your body is a collection of cells and organs. From another, it is a configuration of fields punctuated by brief, weak interactions that produce or absorb ghost particles, most of which exit immediately and never come back. If you zoom out further, past the scale of organisms and planets, you find that the same mechanisms operate in stars, in reactors, in supernovae. Neutrinos are produced whenever certain nuclear reactions occur. Proton-proton fusion, which powers the sun, yields neutrinos. The collapse of a massive star's core dumps most of its energy into a sudden blast of neutrinos. Nuclear reactors on Earth emit streams of antineutrinos as their fuel undergoes fission and subsequent decays. And long before any of these systems existed, The young universe itself created neutrinos in huge numbers when it was still a dense hot plasma. All of this keeps feeding the background. Neutrinos from every era layer on top of one another. Some left their sources only minutes ago. From the core of the Sunday, some have been traveling unhindered since the universe was less than a second old. They do not react strongly with each other. They do not scatter the way photons do in an opaque medium. Once they are free, they travel almost in straight lines unless gravity bends their paths slightly on large scales. The difficulty in studying such particles is obvious. To catch even a few of them, you need to compensate for their reluctance to interact by stacking enormous numbers of potential targets. That is why neutrino detectors are often built as gigantic tanks of water or special liquids, buried deep underground or in ice, shielded from other kinds of radiation. Inside these volumes, every atom is a possible site where a passing neutrino might occasionally decide to interact and leave behind a tiny flash of light or a trace of charged particles. Those rare signals, teased out from background noise, are all we have to reconstruct the behavior of a population that otherwise passes through us unnoticed. The paradox is sharp. On the one hand, neutrinos are practically non-existent at the level of individual experience. In your entire lifetime, only a handful of the trillions upon trillions of neutrinos that cross your body will ever actually collide with one of your particles and announce themselves in any way. On the other hand, they are structurally important for the universe. They influence how stars cool. They affect how elements were synthesized in the first minutes after the Big Bang. They shape the growth of cosmic structures through their collective mass and motion. When you hear that neutrinos pass through a light year of lead without caring, it is easy to dismiss them as irrelevant. When you hear that they outnumber atoms in the universe by vast factors, it is tempting to treat them as some vague background. But precisely because they so rarely interact, any imprint they carry from the past is likely to have survived. Where photons can be scattered, absorbed, and re-emitted many times before reaching us, washing out their original information, neutrinos often travel more directly from their birthplace to our detectors. A particle that barely touches anything is a particle that can preserve memory. Not in the conscious sense, not in any human meaning of the word, but in the way that its energy, direction, and flavor encode what conditions were like at the moment it decoupled from its surroundings. From that perspective, the ghost-like quality of neutrinos is not just an experimental nuisance. It is the key property that lets them function as messengers from times and places that would otherwise remain opaque. They are extremely light points in a ledger that spans from the first fractions of a second after the Big Bang to the present. Each one is a tiny receipt for a transaction in the early plasma, in a stellar core, in a collapsing star. So when we call them ghost particles that fill the cosmos, it is not because they belong to another realm. It is because they occupy the parts of this one that our usual senses and instruments barely touch. They are the particles that pass through you, through the planet, through enormous blocks of matter, carrying whispers from epochs when the universe was still deciding how much imbalance it would allow. At some point, it was not enough to say that ghost particles might exist. Someone had to ask the harder question. If they are really out there, how do we corner something that refuses to touch almost anything at all? The first answer was not an experiment. It was a worry in an equation. In the early decades of the 20th century, physicists were studying beta decay, a process in which a nucleus emits an electron and changes its charge. When they measured the energy of the emitted electrons, they found something uncomfortable. The energies did not come in a single sharp value, as a simple two-body decay would suggest. Instead, they spread over a continuous range. It looked as if energy conservation, one of the most trusted rules in physics, might be violated at the microscopic level. For a while, people entertained that possibility. Maybe the law was not absolute. Maybe something about the quantum world allowed a small leak in the accounting. Then, a different idea appeared. Wolfgang Pauli, an Austrian theorist, suggested that there might be an unseen particle carrying away the missing energy and momentum. It would have to be light, neutral, hard to detect. It would escape quietly, leaving the visible electron with a range of possible energies. He proposed this in a letter written in the early 1930s, addressed almost apologetically to his colleagues. According to later reports, he joked that he had done a terrible thing, introduced a particle that might never be observed. It is one thing to write such a particle into an equation. It is another thing to build an instrument that can see it. For decades, neutrinos remained in that limbo. They were useful to preserve conservation laws. They made the mathematics consistent. But the odds of detecting something that interacts so rarely with matter seemed so low that many considered the effort hopeless. After all, if a neutrino can cross distances of dense material comparable to stars and still not collide, what chance does a laboratory tank have? Then world history shifted the balance of what counted as possible. The mid-20th century was the age of nuclear weapons and nuclear reactors. Humanity had learned to trigger controlled and uncontrolled fission chains. With that came new sources of intense radiation. Bomb tests released brief, monstrous flashes. Reactors produced steady flows of neutrons, gamma rays, and, quietly, antineutrinos from the beta decays of fission fragments. Two physicists, Frederick Reiners and Clyde Cowan, saw something in that new landscape. If each fission in a reactor produced a few antineutrinos, and the reactor sustained an enormous number of fissions every second, then the total number of emitted antineutrinos would be staggering. Even if the probability of interaction with matter was tiny, the sheer flux might still yield a small but detectable rate of collisions in a suitably large target. It was not a gentle idea. People compared it to listening for a gnat's whisper in a hurricane, or trying to spot a single faint spark in a floodlight's glare. To detect antineutrinos near a reactor, you have to sit in the middle of intense radiation fields and still isolate a signal that almost never appears. But the post-war world had something that earlier generations did not. It had technical infrastructure built for bombs and reactors that could be repurposed for more delicate listening. Reiners and Cowan first considered placing a detector near a nuclear test site, hoping to use the brief but enormous flux from an explosion. That plan was eventually abandoned as impractical and dangerous. Instead, they turned to reactors as calmer, continuous sources. They designed an experiment near the Savannah River plant in the United States. The idea was simple in principle and intricate in execution. Antineutrinos emitted by the reactor could occasionally interact with protons in a hydrogen-rich liquid. When that happened, the antineutrino would convert a proton into a neutron and a positron. The positron, being the antimatter counterpart of the electron, would quickly find an ordinary electron in the liquid. The two would annihilate, vanish as particles, and turn into a pair of gamma-ray photons flying off in opposite directions. The neutron, meanwhile, would wander a bit, slow down, and then be captured by a nucleus, emitting another gamma-ray. So the signature of an antineutrino interaction would be a very particular pattern, a prompt flash of gamma rays from the positron annihilation, followed, after a short delay, by another flash from the neutron capture. Two light pulses, separated by microseconds, appearing in coincidence in the detector. Against a random background of radiation, that double flash would stand out as something special. To realize this, they filled large tanks with a substance rich in hydrogen and doped with elements that made neutron capture more visible. They surrounded the tanks with photomultiplier tubes to detect faint flashes of light. They buried the apparatus under shielding to reduce other sources of radiation. And then they let the reactor do what it always does, emitting a storm of particles, most of which they could not use, while they listened for the rare double signals deep in the detector. It is worth pausing on the contrast. The same technology that fed the arms race, that powered the first generation of nuclear weapons, now provided an almost accidental gift: an intense antineutrino source that made a fundamental particle testable. The most violent developments of the century created the environment in which one of the quietest phenomena could finally be seen. In the mid-1950s, after months of data taking and analysis, Reiners and Cowan concluded that they had indeed observed the signature they were seeking. The rate of double flashes changed when the reactor was turned on and off. The timing and energies matched predictions for inverse beta decay. They had directly detected antineutrinos. The ghost in Pauli's letter had produced a measurable trace in a real detector. They sent a telegram to Pauli announcing the result. By then, he was an established figure in physics, and the news that his hypothetical particle had been found in the laboratory closed a circle that had begun in a moment of theoretical discomfort about energy conservation. The neutrino was no longer just a bookkeeping device. It was part of the furniture of reality. The experiment did more than confirm a prediction. It demonstrated a new way of looking. By turning nuclear reactors into neutrino sources and designing detectors tuned to the weak interaction, Reines and Cowan opened an entire field. If antineutrinos from reactors could be observed, then in principle so could neutrinos from the sun, from the atmosphere, from supernovae. The practical challenges remained severe, but the wall between theory and observation had cracked. Recognition was slow. Reines eventually received a Nobel Prize decades later, in the mid-1990s, for his work on the detection of the neutrino. Cowan had died long before and did not share in that late honor. Their story fits a pattern that recurs often in fundamental physics. The payoff for betting on a barely tangible entity can take a lifetime to arrive. For years, the work looks like an elaborate attempt to measure something that may as well not exist. Only later does the community come to see it as the start of a new way of listening to the universe. There is a quiet symbolism in the whole episode. A technology built around controlled fission, born from the same research that made atomic bombs possible, becomes a tool for hearing the faintest whisper in the cosmic background. A device that is in some sense an emblem of human power and threat is repurposed as a lantern aimed at the most elusive components of reality. The method they used also foreshadows a deeper theme in neutrino physics. You cannot see these particles directly, you can only infer their presence from the products of their rare interactions. In the Savannah River experiment, no one ever watched a neutrino entering the tank. They watched light flashes, produced by positron annihilation and neutron capture, and inferred, from timing and coincidence, that an antineutrino must have been there a moment earlier. Everything about the particle's existence was written indirectly into a pattern of ordinary photons. That pattern is fragile. It can be mimicked by background radiation. It requires careful statistical analysis to stand out. It depends on trusting your understanding of nuclear processes in the detector medium. And yet, once enough events are collected, a clear difference appears between reactor on and reactor off. The ghost leaves fingerprints, faint but consistent, on a world otherwise shaped by much louder forces. What Reines and Cowan did, in effect, was to turn human-made nuclear fire into a controlled source of early universe conditions. The beta decays in a reactor are cousins of the processes that happened in the hot, dense plasma of the young cosmos. By watching antineutrinos from those decays, we practice reading a language that was spoken naturally when the universe was still very young. Seen this way, the first successful neutrino detection is less a triumphant end of a search and more the opening of a new chapter. If we can detect particles that almost never interact, then perhaps we can use them as probes of regions that no photon can escape. If we can trust the faint double flash in a tank near a reactor, maybe we can also trust similar patterns coming from beneath mountains, from under ice, from deep mines, from the heart of a collapsing star. The first neutrino hunters were not chasing beauty, they were chasing consistency. They wanted the numbers in their equations to balance. They wanted the principle of energy conservation to hold. But in insisting that a missing quantity be carried by something real, they ended up discovering more than a patch for a puzzle. They found a channel that connects us to events that are otherwise inaccessible. From here on, every time we speak of neutrinos as messengers or witnesses, it is important to remember how reluctant they were to step onto the experimental stage at all. It took the conjunction of theoretical unease, technological upheaval, and patient experimental design to coax even a handful of them into revealing themselves. Once that happened, the idea that neutrinos could be used as a kind of telescope stopped being a fantasy and became a program. The question that follows is simple to phrase and difficult to answer. If we can listen to antineutrinos from reactors, can we also listen to neutrinos from the sunday, from distant supernovae, from the first seconds after the Big Bang? And if so, Can those particles do more than confirm what we already think we know? Could they carry, in the pattern of their arrival and in the details of their properties, a record of the moment when the universe first allowed imbalance to win? It is a strange kind of astronomy that begins not with looking up, but with learning to count brief flashes in the dark, far underground. Once the first antineutrinos had been coaxed into revealing themselves near a reactor, the idea of using neutrinos as messengers from the cosmos stopped being fantasy. If human-made nuclear fire could serve as a source, then so could the natural reactors scattered through the universe. Stars, supernovae, the hot, dense plasma of the early cosmos itself. The question quietly shifted from "do neutrinos exist?" to "what can they show us that light cannot?" The key difference is simple. Light, in the form of photons, scatters very easily in hot, dense matter. Neutrinos mostly do not. In the core of a star like the Sun, photons are born in fusion reactions at enormous temperatures and densities. But each photon is absorbed and re-emitted, scattered and redirected, by charged particles countless times before it works its way off to the surface and then out into space. The journey from core to surface can take a time that, on human scales, might as well be forever. Neutrinos from those same fusion reactions barely notice the surrounding plasma. They interact through the weak force, and that force has a short reach and a small probability. Once a neutrino is produced in the core, it usually flies straight out at essentially the speed of light, passing through the star's dense layers as if they were mist. Where photons give you a view that has been mixed and delayed, neutrinos offer something closer to a direct report. That is the seed of the idea of neutrino astronomy. Instead of relying only on light, you treat neutrinos as another messenger. Not a replacement, a complement, another way the universe expresses what it is doing. The first serious attempt to listen to the Sun using neutrinos took place in an unlikely setting, an old gold mine in the Black Hills of South Dakota. In the late 1960s, Raymond Davis Jr., an American chemist and physicist, installed a huge tank of cleaning fluid deep underground in the Homestake mine. The fluid was rich in chlorine atoms. The plan was simple in outline. Occasionally, a solar electron neutrino, coming from the fusion reactions in the Sun's core, would hit a chlorine nucleus and turn it into an argon nucleus, emitting an electron in the process. The argon atoms would be chemically identical to the chlorine atoms in many respects, but not in all. They were noble gas atoms trapped in a liquid. With clever chemistry and painstaking effort, Davis and his colleagues could periodically flush the tank with helium gas and extract the tiny number of argon atoms that had been created since the previous run. Each argon atom represented a neutrino interaction that had happened in the tank. The scale of the experiment was almost absurd. The tank contained about 600 tons of perchloroethylene. From that huge mass, in an entire month, they might expect to extract only a few dozen argon atoms if the theory of solar fusion and neutrino production was correct. Each atom was, in a sense, a recorded whisper from the heart of the Sun, captured deep under a mountain. But when Davis tallied the counts and compared them to the theoretical predictions, something unsettling emerged. The number of detected neutrinos was not just a bit off. It was roughly 1/3 of what standard solar models implied it should be. Run after run, over years, the result held. The Sun, as seen in neutrinos, seemed dimmer than expected. This became known as the solar neutrino problem. Either our understanding of the Sun's interior was wrong, or our understanding of neutrinos was incomplete. There was no trivial way out. The nuclear reactions that power the Sun also determine its luminosity, radius, and surface temperature. Those were well matched by models. To adjust the neutrino production downward without breaking everything else was hard. For decades, the discrepancy remained. Other experiments joined the effort, using water and gallium, and different detection techniques, and they also tended to see fewer neutrinos than predicted, though the details varied. The problem sat there like a quiet accusation. Either you have misunderstood your nearest star, or the ghost particles you thought you knew are doing something you did not anticipate. During those years, Another line of neutrino observation was quietly preparing to make history. In Japan, in an underground mine near the town of Kamioka, a large detector had been built initially to search for proton decay, a hypothetical process predicted by some grand unified theories. The detector, called Kamiokande, consisted of a large tank of ultra-pure water lined with photomultiplier tubes. When a charged particle moved through the water faster than light can travel through that medium, it produced a faint cone of blue Cherenkov radiation, which the photomultipliers could pick up. That setup turned out to be sensitive not only to hypothetical proton decays but also to neutrinos. When a neutrino happened to scatter off an electron or nucleus in the water, it could produce a charged particle, whose track generated Cherenkov light. By recording the pattern and timing of the photomultiplier hits, physicists could infer the direction and energy of the incoming neutrino to some extent. On a February night in the year 1987, that detector was quietly watching its volume, as it always did, waiting for rare events. In a nearby Soviet laboratory, in an American mine, other neutrino detectors were doing the same. Far away, in a small companion galaxy called the Large Magellanic Cloud, a massive blue supergiant star had reached the end of its life. Its core collapsed. A shockwave formed. In the process, a flood of neutrinos carried away most of the gravitational binding energy of the core, escaping almost unhindered from the dense interior. Those neutrinos raced across space for about 160,000 years, almost all of that journey uneventful. Then, within a window of a few seconds, they arrived at Earth. The majority passed straight through the planet as usual. A tiny fraction happened to interact in the huge detectors waiting underground. At the Kamiokande detector in Japan, a burst of events appeared. 11 neutrino interactions recorded over about 13 seconds. At roughly the same time, other detectors registered their own handfuls of events. The timing and energies matched what one would expect from a core collapse supernova at the distance of the Large Magellanic Cloud. A few hours later, astronomers using optical telescopes noticed a new bright spot in that galaxy. The visible light from what would be called supernova 1987A had finally broken free and reached Earth. The sequence was important. Neutrinos arrived first. By hours, light came later. That was not because neutrinos outran photons in a vacuum. It was because in the collapsing star, neutrinos escaped quickly from the dense core, while photons had to fight their way out through layers of material that remained opaque for a time. Once the shockwave and expansion had progressed enough, the outer layers became transparent, and the light could stream out. For the first time in history, a supernova in another galaxy had been observed not just in light but in neutrinos. For the first time, the death of a star had sent a neutrino telegram ahead of its visible display, and our detectors were sensitive enough to catch it. It was a modest dataset, just a few dozen events spread across several experiments. But each of those events came from interactions with neutrinos that had been inside the core of a massive star at the instant of its collapse. This is what it means for neutrinos to act as time telescopes. Because they escape so quickly and travel without much disturbance, they preserve information about a process at the moment it happens. Because they stream out from dense interiors that light cannot immediately leave, they extend our observational reach inward as well as backward. You can think of the supernova neutrino burst as a private message, a kind of early notice whispered across the cosmos. Before the sky offers you the spectacle of a new star flaring into view, the neutrinos have already told you that the core has collapsed, that nuclear burning has ended, that the object's fate is sealed. If we had been equipped then with an automated alert system, the neutrino detectors could have signaled astronomers to point their telescopes at the right patch of sky before the light even began to rise. Since that event, the concept of multi-messenger astronomy has taken root. The idea is that the universe does not communicate in a single channel. Photons carry one kind of information. Neutrinos carry another. Gravitational waves add their own quiet record of motion and collapse. Charged cosmic rays write yet another story. By combining these, we can reconstruct events with a richness that no single messenger can provide. Neutrinos have a particular strength in this ensemble. They are sensitive to the weak interaction and to gravity. not to electromagnetism. They therefore see aspects of processes that light does not. In a core collapse supernova, they account for the majority of the energy release. In the first seconds after the Big Bang, they decouple from the plasma earlier than photons do. When we detect them from such events, we are not just adding another color to an image, we are adding a different layer of physical history. In practice, turning neutrinos into time telescopes requires detectors that are both patient and huge. Structures like Super Kamiokande in Japan, IceCube at the South Pole, and others are designed to wait for years, accumulating tiny signals from vast numbers of potential interactions. The Earth becomes part of the apparatus. The planet's bulk filters out many background particles, so that what remains in deep underground or under ice volumes is more likely to be of cosmic origin. Atmospheric neutrinos, produced when cosmic rays strike the upper air, arrive from all directions, day and night, providing a constant background and a tool for studying oscillations. Solar neutrinos arrive on a more directed stream from the Sunday. Rare bursts from distant supernovae, like the one in the Large Magellanic Cloud, arrive as sharp spikes. High-energy neutrinos from active galactic nuclei or gamma-ray bursts may occasionally leave long, bright tracks in the detectors. Each of these populations probes a different time and place. Solar neutrinos carry information from the core of our star as it is now. Atmospheric neutrinos reflect ongoing interactions above us. Supernova neutrinos give short, intense glimpses of stellar death, with the delay between neutrinos and light encoding the internal opacity of the progenitor star. Relic neutrinos from the early universe, if we can ever detect them directly, would reach much farther back, into the first second or so of cosmic history. What ties all these together is the way neutrinos decouple. Once they stop scattering significantly, they free stream. That moment of decoupling defines a surface in space-time from which they travel to us. When we observe them, we are looking back to that surface. It is not a surface of last scattering for light, like the one we see in the cosmic microwave background. It is something earlier, deeper in the timeline. So when we say that neutrinos become time telescopes, we are not using a poetic shortcut. We are describing a real mapping between detection and past conditions. A neutrino produced in the core of a star or in the infant universe travels outward almost unchanged. When, much later, it interacts in a tank of water or ice, it triggers a small cascade of ordinary particles. We record that cascade and, using our models, reconstruct where and when the neutrino must have come from. The detector becomes a screen on which ancient events leave fresh marks. The supernova in the Large Magellanic Cloud was a proof of concept on a cosmic scale. It showed that neutrino detectors could catch signals from outside our own solar system. It demonstrated that the timing of neutrino and photon arrivals carries information about the dynamics of stellar collapse. It hinted that if we can improve sensitivity and coordination, the next nearby supernova could provide a detailed movie of neutrino emission over tens of seconds, revealing aspects of physics at densities and temperatures we cannot reproduce on Earth. Beyond individual events, there is a more ambitious dream. Just as the cosmic microwave background gives us a snapshot of the universe when it was a few 100,000 years old, a cosmic neutrino background would, in principle, carry a snapshot from when the universe was less than a second old. The neutrinos that decoupled then have been streaming through space ever since, cooled and diluted by expansion, but still present. They form an invisible fog, permeating every cubic centimeter of space. We do not yet have the ability to detect those relic neutrinos directly. They are far colder and slower than the neutrinos from the Sun or supernovae. Their energies are tiny. Their interactions are even rarer. But the same logic that turned a chlorine tank in a mine into a solar neutrino observatory and a water tank in Japan into a supernova detector suggests that with enough ingenuity, we might one day capture a handful of those ancient particles. If that happens, neutrinos will have extended our time telescope all the way back to the universe's first instance of imbalance. They will not show us a picture in any familiar sense. There will be no image to look at, only a distribution of energies, directions, and flavors. But encoded in those numbers will be the record of how the early plasma behaved, how symmetries were enforced and broken, how matter and antimatter first fell out of perfect balance. For now, we live in the middle of that story. We operate detectors in mines and ice and underwater caves, watching for rare flashes that mark the passage of particles born long ago or far away. We treat each recorded neutrino as a small note in a long ledger. Piece by piece, they let us reach past the surface of stars and beyond the wall of the cosmic microwave background toward the opaque first moments when the universe began to decide which possibilities to keep and which to erase. The flashes we catch now are like notes written long after the first decisions were made, still helpful, but already echo. To understand what neutrinos might show us about the very beginning, it helps to look at the best baby picture of the universe we have so far. It is not a photograph in the usual sense. It is a sky map of microwaves, a pattern of tiny temperature differences spread across the whole dome above our heads. This is the cosmic microwave background, the afterglow of a time when the universe was much younger and simpler than it is now. In the earliest moments, the cosmos was hot, dense, and opaque. Matter existed as a plasma of free protons, electrons, and light. Photons bounced off charged particles constantly. They could not travel far without scattering. The universe was bright from the inside, but there was no such thing as a clear line of sight. It was more like being inside a glowing fog, where light keeps ricocheting and never gets out. As the universe expanded, it cooled. Over time, the average energy of particles dropped. Eventually, there came a moment when protons and electrons could combine and stay together as neutral hydrogen atoms without being immediately torn apart by energetic photons. When that happened, free electrons became rarer. With fewer charged particles available to scatter from, photons finally began to move more freely. This transition is sometimes called recombination, even though it was really the first time atoms formed in large numbers. The age of the universe at that moment was on the order of a few 100,000 years, usually estimated to be about 380,000 years after the beginning. The temperature had fallen to a few thousand degrees above absolute zero, roughly what one would find on the surface of a relatively cool star. The photons that were set free then have been traveling ever since. As space expanded, their wavelengths stretched. What began as visible and infrared light shifted into the microwave range. Today, those photons make up a nearly uniform background with a temperature of about 2.7 degrees above absolute zero, arriving at us from every direction. When we map that background, we do not see a perfectly smooth field. There are tiny variations in temperature and intensity, differences of only a few parts in 100,000. Those small mottlings are important. They reflect slight differences in density and pressure in the early plasma. Regions that were slightly denser seeded the later formation of galaxies and clusters. Regions that were slightly less dense became voids. The cosmic microwave background is often described as a baby photo because it shows the universe when it was very young, with the first hints of structure already present. But it is not a picture of the very beginning. It is a picture taken hundreds of thousands of years into the story. Anything that happened before that time is blurred out in this image. The photon fog of the earlier universe has wiped away direct traces of those first instants. We can infer some things indirectly by modeling the physics, but we cannot simply look before recombination with light. That is the limit of photon-based astronomy. The screen of last scattering is as far back as visible and microwave light can show us. This is where neutrinos re-enter the narrative. Long before photons decoupled from matter, neutrinos had already done so. In the first fractions of a second after the beginning, when temperatures were around tens of billions of degrees, neutrinos were in thermal equilibrium with the rest of the plasma. They collided, exchanged energy, and contributed to the overall dynamics. As the universe expanded and cooled, the rate of interactions dropped. At around the 1 second mark, give or take, neutrinos effectively stopped interacting, often enough to stay in equilibrium. They decoupled. From that moment on, most of them simply streamed outward, barely touching anything. Those relic neutrinos did for their epoch what relic photons did later for recombination. They carried away a snapshot of conditions at the time they last scattered. The difference is that their snapshot is much earlier. Where the cosmic microwave background shows you the universe at hundreds of thousands of years old, the cosmic neutrino background, if you could see it, would show you the universe at about 1 second old. Since then, these neutrinos have been traveling through space, cooled and diluted by expansion. Their average energy is now extremely low, corresponding to a temperature a bit below that of the microwave background. They form an almost undetectable fog, filling every region of space, including the space around and inside you, right now, as you sit wherever you are. Relic neutrinos from the first second after the beginning are drifting through your body. They carry information about a time when protons and neutrons were still being assembled from quarks, when matter and antimatter were annihilating in huge quantities, when the first tiny imbalances in particle numbers were being established. We already have indirect evidence that this background exists. When cosmologists fit models of the early universe to observations of the cosmic microwave background and the distribution of galaxies, they find that the data are best explained if there were a certain number of light, freely streaming species present at early times. Neutrinos fit that description well. Their presence affects how quickly the universe expanded and how sound waves in the plasma evolved before recombination. The pattern of peaks and troughs in the microwave background power spectrum carries the imprint of those effects. But indirect evidence is not the same as direct detection. We have seen the influence of relic neutrinos on other things. We have not yet caught one of them in the act. Doing so is extraordinarily difficult. These particles are cold, slow, and interact even more rarely than the neutrinos we detect from the sun or reactors. Their energies are so low that conventional detection methods, which rely on measurable recoil or Cherenkov light, are effectively blind to them. One proposed route around this uses a particular beta decay process. Consider a radioactive nucleus like tritium, a heavy form of hydrogen with 1 proton and 2 neutrons in its nucleus. Tritium undergoes beta decay. A neutron converts into a proton, emitting an electron and an antineutrino. The energies of the electrons follow a continuous spectrum up to a sharp endpoint determined by the energy released in the decay and the neutrino mass. If a relic neutrino from the cosmic background were to interact with a tritium nucleus, it could induce the inverse process. The neutrino is absorbed, the nucleus changes, and an electron is emitted without a neutrino in the final state. Because no neutrino carries away energy, the emitted electron would have a slightly higher energy than those from ordinary beta decay. In principle, by measuring the electron energy spectrum with extreme precision and looking for a tiny bump just above the usual endpoint, one could infer the presence of captured relic neutrinos. Experiments like this would need to control and understand their environment to an almost unsettling degree. The source has to be large enough that even a minuscule capture rate becomes measurable over years. The detectors must resolve energy differences on the scale of a tiny fraction of an electron volt, something like detecting a slight change in pitch in an enormous, constant noise. Backgrounds from other radioactive decays, cosmic rays, and instrumental noise must be suppressed. And even if all that works, the expected number of relic neutrino events per year is small, perhaps on the order of a handful for a carefully designed setup. This is the dream of a 1-second snapshot. Not a picture you can hang on a wall, but a set of numbers slowly accumulated over time. Each detected relic neutrino would correspond to one interaction with a nucleus in the detector. Its energy and perhaps its direction would encode a piece of information about the state of the universe when it decoupled. No single event would tell you much. But as with the cosmic microwave background, where millions of measured points build up a map, many relic neutrino detections could, in principle, reconstruct statistical properties of that early plasma. With such a snapshot, we would no longer be limited to extrapolating from hundreds of thousands of years after the beginning backward. We would have a direct probe of physics at around 1 second old. Models of how matter and antimatter fell out of balance, how neutrino flavors behaved, how new physics beyond the standard model might have manifested, could be tested against actual data from that time. The difference between a world with and a world without that information is subtle but profound. Right now, our account of the first second is a blend of well-grounded physics and carefully extended speculation. We know how the strong, weak, and electromagnetic forces behave at energies we have reached in accelerators. We have measurements of particle properties. We can plug those into equations and simulate the early universe with some confidence. But the time window in which the crucial asymmetry between matter and antimatter was established is precisely the window where small corrections or new interactions could have outsized effects. Relic neutrinos were present and active participants in that era. The way they decoupled, the exact number of species, their masses, and any subtle differences in how they and their antiparticles behaved, all feed into the final state of the universe. To measure their background directly would be to ask the universe to show us its rough draft, rather than only the final edited version. There is also a psychological angle to this pursuit. The cosmic microwave background already pushes our intuition. It asks us to imagine a time when no stars existed, no galaxies, just a hot, nearly uniform fog. To go further back, to a time when even neutral atoms had not yet formed, feels like stepping off the last solid ledge before the unknown. The idea that a kind of particle wind from that moment is still blowing through us, silent and omnipresent, stretches the sense of what now means. If we succeed in detecting that wind, the effect will not be theatrical. There will be no dramatic images, no obvious spectacle. There will be graphs and uncertainties and careful cross-checks. But beneath that, there will be an almost quiet shift in how we relate to the beginning. Instead of talking about the first second as a theoretical construct, we will have data points anchored in that interval. We will be listening, in a very literal way, to the thermal noise of an infant universe. And even if the results turn out to be fully consistent with our current expectations, that consistency will have weight. It will say that the path from imbalance to structure, from a nearly symmetric plasma to a matter-dominated cosmos, passed through a stage we can now see with two different kinds of messengers: photons from hundreds of thousands of years later, neutrinos from around 1 second after the start. From there, the questions we can ask become sharper. If the relic neutrino background matches a picture in which neutrinos are exactly as simple as the standard model allows, then we are pushed to look elsewhere for the source of the matter asymmetry. If instead we find small deviations, hints of extra species or unexpected behavior, then the first second will have spoken up, and neutrinos will have justified their reputation as quiet archivists of the universe's earliest fracture. The universe's earliest ledger is written as much in what was destroyed as in what managed, somehow, not to vanish. At high enough energies, the distinction between matter and light blurs. Einstein's famous relation, usually written as energy equals mass times the speed of light squared, means that in a hot, dense environment, energy can turn into particles, and particles can turn back into energy. When conditions are right, a single energetic photon can transform into a pair, a particle and its antiparticle. An electron is born together with a positron. A proton has an antiproton. Neutrons have antineutrons. Every familiar constituent of matter has a mirror partner with the same mass and opposite charges. For a long time, this symmetry was a mathematical curiosity. In the late 1920s, Paul Dirac tried to write an equation that would describe electrons in a way that respected both quantum mechanics and special relativity. The equation worked, but it came with a troubling feature. It allowed negative energy solutions. Instead of discarding them as nonsense, Dirac interpreted these as signs of a new kind of particle, one that would behave like an electron but with positive charge. At first, that interpretation looked like a bold guess. Then, in the early 1930s, Carl Anderson, studying cosmic ray tracks in a cloud chamber at the California Institute of Technology, saw something unexpected. A curved trail in his photographs corresponded to a particle with the same mass as an electron, but bending in the opposite direction in a magnetic field. It was, as he later understood, the positron, the first confirmed antiparticle. With that, antimatter stopped being a theoretical trick and became part of the observed world. The idea that every particle has a partner was no longer just a convenient symmetry. It was a feature of reality, And if that symmetry held in the extreme conditions of the early universe, something unsettling followed. Right after the beginning, when temperatures and densities were far beyond anything we can reproduce on Earth, energy in the primordial plasma would have been constantly turning into pairs of particles and antiparticles, and those pairs would have been annihilating back into photons. In a perfectly symmetric universe, each creation would be matched either immediately or eventually by a destruction. For every electron, a positron; for every proton, an antiproton. As the universe expanded and cooled, most of those pairs would meet and vanish into radiation. If the symmetry had been exact, if nature had treated matter and antimatter with perfect fairness, almost nothing would have been left. A few photons, relic neutrinos, maybe some other light particles, diluted by expansion. No stars, no chemistry, no observers. The universe would have been clean in a way that leaves no room for questions. And yet, that is not what we see. We live in a cosmos filled with matter, galaxies, gas, planets, bodies. Large-scale surveys do not show alternate domains of antimatter galaxies separated by annihilation boundaries. Gamma-ray observations constrain any such boundaries to be so distant and diffuse that within the observable universe, matter clearly dominates. The usual way physicists summarize the situation is simple and stark. In the early universe, for roughly every billion matter-antimatter pairs that annihilated, there was one extra matter particle left over. That tiny excess, that surplus of one part in about 1 billion, is what all the baryonic matter in the cosmos is built from. It is hard to feel how small that imbalance is. Imagine stacking 1 billion coins on a table, half designated as matter, half as antimatter. Each matter coin paired with an antimatter partner. Now imagine almost every pair meeting and disappearing, leaving only a single unpaired coin behind. That lonely survivor would be the seed of everything that followed. This is what people mean when they speak of a universe that should have been empty. The known laws of physics, if applied in a straightforward way to the beginning, suggest that matter and antimatter ought to have been produced in equal quantities. Given enough time, they should then have annihilated almost completely. But the universe did not choose that path. It allowed, or generated, a very slight bias. And that bias accumulated into the world we know. The puzzle of where that bias came from is called the matter-antimatter asymmetry problem, or sometimes the baryon asymmetry problem, because protons and neutrons are baryons. It is one of the central open questions in cosmology and particle physics. Standard calculations, using the interactions we have measured in laboratories, do not yet provide a satisfactory explanation for the size of the asymmetry. The symmetry between matter and antimatter, elegant as it appears, is not inviolable. We know this from experiments. Dirac's equation, combined with quantum field theory, predicts pair creation and annihilation. When a particle meets its antiparticle, they can destroy each other, converting their mass into energy in the form of photons. That is not just a thought experiment. It is the basis of a medical imaging technique used every day around the world. In positron emission tomography, or PET scanning, a patient is given a radio tracer that emits positrons. Each positron travels a short distance in the tissue before encountering an electron. When they meet, they annihilate. Their mass is turned into 2 gamma-ray photons that fly off in nearly opposite directions with a well-defined energy. A ring of detectors around the patient records those photons. By collecting many millions of these detection events and reconstructing where in the body the annihilations occurred, doctors can build detailed images of metabolic activity. From the patient's perspective, nothing dramatic happens. They lie still in a machine. Time passes. Outside, electronics quietly tally the signals from countless matter-antimatter encounters taking place inside their tissues. It is an intimate, everyday example of a process that, at cosmic scales, nearly erased the universe. The contrast is sharp. In the hospital, annihilation is a tool. In the early universe, annihilation was almost the default fate of everything that existed. The rule was destruction. The exception was survival. The interesting question is, why any exception occurred at all? The general framework for thinking about this goes back to Andrei Sakharov, who, in the late 1960s, laid out conditions that any successful explanation for the baryon asymmetry must satisfy. They involve violations of certain symmetries, including the combined charge and parity symmetry, and the requirement that some interactions fell out of thermal equilibrium in the right way. The details are technical. The core idea is simple. The laws of physics must somewhere contain a small preference for processes that produce matter over processes that produce antimatter, and the early universe must have provided a setting in which that preference could show itself. We have seen hints of such preferences. Experiments with neutral kaons in the 1960s and with B mesons decades later have observed violations of charge parity symmetry, situations where particles and antiparticles do not behave as perfect mirror images in their decays. More recently, asymmetries have even been observed in decays of certain baryons themselves. But when physicists take the size of the known symmetry violations in quark systems and plug them into cosmological models, the result falls far short. The amount of asymmetry they produce is tiny compared to the 1 in a billion imbalance we actually infer from observations. The known sources of matter-antimatter bias are real, but they seem too weak to account for a universe filled with galaxies instead of pure radiation. This gap between what we observe and what our current theories can explain is where neutrinos reappear, waiting quietly at the edge of the story. In the dense plasma of the first seconds, neutrinos were abundant. They interacted with electrons, positrons, quarks, and other particles. If neutrinos or their heavier cousins behaved differently from antineutrinos in some subtle way, if there was an asymmetry in their interactions or decays that could feed into an overall excess of matter over antimatter in the lepton sector. Later, through processes that convert lepton number into baryon number, that excess could be transferred into the protons and neutrons that make up ordinary matter. From that angle, the 1 in a billion surplus is not just a lucky accident. It is the outcome of microscopic processes in which the universe, very early on, allowed a tiny unfairness to creep into what would otherwise have been a perfectly balanced annihilation. Neutrinos, being among the first particles to decouple and free stream, are especially well placed to carry a record of those processes. The pattern of their masses, the way they oscillate between flavors, any differences in the behavior of neutrinos and antineutrinos all become potential fingerprints of how the universe chose matter over emptiness. It is unsettling to think that everything familiar is built on such a slim margin. Every structure you see, every object you touch, every thought you have, depends on the fact that for roughly every billion particle-antiparticle pairs at the beginning, there was one extra particle left without a partner. Without that slight numerical imperfection, the most accurate description of the universe would be silence. And yet, that is where we find meaning. Not in a perfectly symmetric cosmos where nothing lasts, but in a universe that allowed a fracture in the balance, then amplified it. The task now is to read that fracture not just as a poetic image, but as a physical event. Somewhere in the behavior of fields and particles, somewhere in the logs of those first seconds, lies the mechanism that tipped the scales. Neutrinos, almost indifferent, passing through everything, may be among the few remaining witnesses with memories from that time. Confessions do not arrive as grand speeches. They slip out in small imbalances, in tiny preferences that should not exist and yet do. For a long time, physics believed that nature was, at its core, indifferent to certain choices we make, left or right, matter or antimatter. Reverse all of those labels in an equation, and the outcome, people thought, should look the same. Symmetry was not just an aesthetic preference, it was a guiding principle, a quiet assumption that the universe did not favor a particular hand or a particular charge in the fundamental rules. Take the idea of parity, usually called p-symmetry. Imagine standing in front of a mirror. The image on the other side swaps left and right. If you raise your right hand, the reflection raises its left hand. The mirror world looks familiar enough that you might assume the laws of physics would work just as well there. Drop a ball. Fire a rocket. Spin a top. The mirrored versions should behave identically as long as you flip every left into a right and every right into a left. That was parity symmetry, the belief that nature does not care which hand you use. Then there is charge conjugation, usually called C-symmetry. This is the operation that swaps particles with their antiparticles. Electrons become positrons, protons become antiprotons. Every charge flips sign. If you take a process made of ordinary matter and replace everything with its antimatter partner, the old assumption was that nature would treat that mirrored process in the same way. Matter and antimatter would be equal in the eyes of the laws. For a while, this faith in symmetry held. Many interactions in nature respect both P and C. It felt natural to assume that what we saw in those cases was universal. Symmetry was comfort. It implied a kind of fairness in the underlying rules, even if the universe around us looked messy. The first serious crack arrived not in the sky, but in a cold laboratory. In the mid-1950s, two theorists, Tsung-Dao Lee and Chen-Ning Yang, examined the weak nuclear force, the interaction responsible for certain kinds of radioactive decay. They noticed that, unlike the strong and electromagnetic forces, the weak interaction had not been thoroughly tested for parity conservation. It was as if everyone had assumed that p-symmetry must hold there too, without actually checking. They suggested that perhaps parity could be violated in weak processes. It was a daring suggestion, not because the mathematics forbade it, but because so much intuition was tied up in the idea that nature would not distinguish left from right in any deep way. To test their proposal, they turned to an experimentalist whose precision and tenacity were legendary, Chien-Shiung Wu. Wu designed an experiment using a radioactive isotope called cobalt-60. These nuclei decay by emitting electrons, a form of beta decay governed by the weak force. The key idea was to align the spins of a large number of cobalt nuclei using a strong magnetic field and very low temperatures, cooled almost to absolute zero. If parity were conserved, the emitted electrons should be equally likely to fly out in any direction relative to the spin alignment. The distribution would be symmetric in the mirror. Carrying out the experiment was a technical feat. Cooling the sample to such low temperatures, maintaining the alignment, measuring the directions of the emitted electrons with sufficient accuracy, all required careful work and repeated checks. Wu and her collaborators pushed through the difficulties. When the data came in, the result was unambiguous. The electrons did not come out symmetrically. They preferred one direction relative to the nuclear spin over the opposite. It was as if nature said, quite clearly, that left and right are not equivalent in the weak interaction. The mirror world is not a valid twin. Parity, at least for this force, is broken. The shock of this result rippled through physics. An assumption that had felt almost moral in its certainty turned out to be wrong in a specific, measurable way. The universe did care which hand you used, at least when it came to certain decays. Wu's experiment was announced publicly in the late 1950s. Li and Yang received the Nobel Prize soon after for their theoretical insight. Wu's name was, notoriously, missing from the list, an omission that has since become a symbol of both her importance and the inequities in how recognition is distributed. In a way, even the history of that discovery carries its own asymmetry. Parity's fall did not mean that all hope for symmetry was gone. Physicists noticed that if you combined P with C, replacing every particle with its antiparticle and flipping left and right simultaneously, many processes still seemed symmetric. Perhaps the universe did not respect P or C individually, but respected CP together. The mirror world made of antimatter might still behave like our own. That hope lasted only a few years. In the early 1960s, experiments with neutral kaons, particles made of a quark and an antiquark, uncovered something stranger. Neutral kaons have a peculiar property. They can oscillate between a particle state and its antiparticle state as they travel. They also decay into multiple possible final states. James Cronin and Val Fitch, among others, studied these decays in detail. If CP symmetry were exact, Certain decays should either not occur or should occur in perfectly balanced ways between kaons and antikaons. What the experiments found was a small but definite mismatch. Some decays that should have been forbidden by CP symmetry were observed. The rates for processes and their CP mirrored versions were not exactly equal. This phenomenon, called CP violation, meant that even the combined operation of swapping left and right and exchanging matter with antimatter does not always leave the laws unchanged. Nature, at least in the weak interaction, has a built-in bias. It treats matter and antimatter slightly differently. The universe, in that sense, broke its own declared symmetries. Cronin and Fitch were later awarded a Nobel Prize for this discovery. The magnitude of the observed CP violation in neutral kaon decays is small. The effect shows up in subtle differences in decay rates and time evolutions. But small is not the same as unimportant. It is proof that the rules contain a preference, even if that preference is modest. For the problem of why the universe contains more matter than antimatter, this was both a promise and a disappointment. On the promising side, it provided a concrete mechanism by which symmetry could be broken in the right kind of way. On the disappointing side, the numbers did not add up. Calculations based on the amount of CP violations seen in kaons and later in B mesons suggest that the resulting matter-antimatter imbalance would be far smaller than the 1 in a billion surplus. We actually need to explain the cosmic inventory. The universe had confessed to breaking symmetry, but the confession seemed incomplete. Still, the principle was established. The early universe did not have to be fair in every interaction. Under the extreme conditions of the first seconds, small asymmetries in decay probabilities and scattering rates could accumulate into large macroscopic consequences. The crucial question became where else such asymmetries might hide. That is where neutrinos re-enter, once again, as quiet suspects. Just as quarks can exhibit CP violation in their mixing and decays, so too can neutrinos, in principle, in the way they oscillate between flavors. If there is a phase in the neutrino mixing matrix that leads to different behavior for neutrinos and antineutrinos as they propagate, then the lepton sector might harbor the stronger symmetry breaking that the quark sector seems to lack. In simpler terms, if neutrinos change identity with a bias that their antiparticle versions do not share, then the universe gains a tool to favor leptons over antileptons in the early plasma. Through processes that link lepton number to baryon number, that initial lepton asymmetry can then be converted into the baryon asymmetry we see now. This is the core of many leptogenesis scenarios, which we will come back to. But before diving into those models, it is worth staying a little longer with the emotional weight of what symmetry breaking means. In human stories, symmetry often stands for justice, for balance, for some ideal of fairness. In physics, symmetry is a more neutral concept, but it carries some of the same psychological comfort. To discover that the universe has built-in asymmetries can feel like learning that the foundation stones of reality are slightly tilted. The experiments that revealed P violation, C violation, and CP violation did not do so with dramatic fireworks. They did it with careful counts, slight excesses in one direction, tiny differences in decay patterns, plots that do not line up perfectly with mirrored versions. At the level of individual events, each electron, each kaon, is just one more point. Only when you accumulate enough statistics does the pattern reveal a bias that no simple symmetry can explain away. In that sense, the universe's first confession is not a single moment. It is a collection of small misbehaviors, distributed across countless interactions, that collectively say, left is not the same as right. Matter is not treated exactly like antimatter. The mirror world is not fully equivalent to ours. The early universe, operating on these rules at terrifying temperatures and densities, had room to implement a preference. Seen from here, that preference is not an abstract quirk. It is the difference between a cosmos that erases itself and one that leaves room for structure. The same asymmetries that offend our sense of perfect symmetry also underpin our existence. Every galaxy is, in a way, a monument to the fact that CP symmetry is not exact. The task of modern experiments is to map these asymmetries more completely. In quark physics, that means measuring CP-violating phases in different systems and checking whether other sectors of the theory behave consistently. In neutrino physics, it means sending beams of neutrinos and antineutrinos over long distances, comparing how their flavors change, searching for any sign that they, too, violate CP in a way that could drive leptogenesis. If neutrinos do turn out to have large CP-violating effects in their oscillations, it will deepen the sense that these ghost particles are not just passive bystanders. They will look more like agents in the story of the universe's first broken symmetry. If, on the other hand, the measured phases turn out to be small, we will be left with a sharpened mystery. Somewhere, the universe tilted the scales. If it was not mainly in quarks or in the known neutrinos, then it may lie in heavier, earlier particles we no longer see directly. Either way, the logic stands. The universe did not preserve the naive symmetries we once thought were sacred. It broke them in specific, measurable ways. What we are doing now, with underground detectors and long baseline beams and careful analyses, is not imposing asymmetry from outside. It is listening for how the universe itself first admitted, through its own behavior, that perfect balance was never the plan. The universe did not just tilt its rules in favor of matter. It handed that tilt to particular particles and asked them to carry it forward, quietly, over cosmic time. Neutrinos, for a while, were not considered important enough for such a task. In the original version of the Standard Model, the framework that catalogues the known particles and forces, neutrinos were written in as massless. Elegant, simple, and convenient. They came in three types, or flavors, paired with the electron and its heavier cousins, the muon and the tau. They interacted only through the weak force and gravity. They were difficult, almost impossible, to detect. In the equations, setting their mass exactly to zero made life easier and did not seem to contradict any direct observation. The solar neutrino problem should have been a warning that something in that picture was incomplete. For decades, experiments looking for neutrinos from the Sun consistently found fewer electron neutrinos than models of solar fusion predicted. One could blame the Sun, or the nuclear physics inside it. But those models also successfully explained the Sun's brightness, size, and longevity. The mismatch refused to go away. For a long time, the discrepancy was treated as an annoyance rather than a crisis. The Standard Model was astonishingly successful in other domains. It predicted the existence of particles that were later found at colliders. It described electromagnetic, weak, and strong interactions with mathematical precision. Compared to that, a factor of about a third missing in solar neutrino counts looked like a small, local glitch. The real turning point did not come from the Sun at all, but from the atmosphere above our heads. When high-energy cosmic rays, mostly protons, collide with atoms in the upper air, they produce showers of secondary particles. Among those secondary products are pions and kaons, which decay into muons and neutrinos. Those muons then decay further, also producing neutrinos. The result is a steady rain of atmospheric neutrinos arriving at Earth from all directions. If you place a large neutrino detector deep underground, shielded from most other radiation, you can use those atmospheric neutrinos as a kind of natural beam. Some come from directly overhead, having traveled only tens of kilometers through the atmosphere before reaching the detector. Others arrive from below, having crossed the entire diameter of the Earth. If neutrinos behaved exactly as the Standard Model originally suggested, you would expect the number of muon neutrinos to be the same from both directions, once you have accounted for the geometry of the situation. In the late 1990s, the Super Kamiokande detector in Japan provided a very different answer. This enormous tank of ultra-pure water, lined with thousands of light-sensitive tubes, sat under a mountain, watching for tiny flashes of Cherenkov light from particles moving faster than light does in water. When a neutrino interacted in the tank, it could produce a charged lepton whose track would generate such a flash. By studying those flashes, researchers could estimate the type and direction of the incoming neutrino. They found that muon neutrinos arriving from above were more common than muon neutrinos arriving from below. The upgoing muon neutrinos, which had traveled a much longer path through the Earth, were somehow disappearing en route. Electron neutrinos, by contrast, did not show the same suppression. The pattern was not random. It changed with the neutrinos' energies and with the angle from which they entered the detector, in a way that matched a very specific hypothesis. The missing neutrinos had not actually vanished. They had changed identity. This is what neutrino oscillation means. Neutrinos come in three flavors: electron, muon, and tau. But those flavors are not the states that have definite mass. Instead, the flavor states are quantum superpositions of three mass states. As a neutrino moves, the components corresponding to different mass states evolve at slightly different rates. The quantum interference between them causes the neutrino's flavor to change with distance and energy, like a pattern of beats in overlapping waves. If you create a neutrino in a pure electron flavor, say in a nuclear reactor or in the sun, it does not stay purely electron-flavored as it propagates. After a certain distance, the probability that it will be detected as a muon or tau neutrino instead grows. After another interval, the probabilities shift again. The oscillation length depends on the differences between the squared masses of the neutrino mass states and on the neutrino's energy. For this behavior to be possible, neutrinos must have non-zero masses. And the flavor states must be mixtures of mass states with specific mixing angles. That is a fundamental departure from the original Standard Model, which treated neutrinos as exactly massless and flavor-aligned with mass. Oscillation is, in effect, the universe's way of telling us that those assumptions were wrong. Super Kamiokandé's atmospheric neutrino results were a clear sign that muon neutrinos were changing into other flavors during their journey through the Earth. The solar neutrino problem, when revisited in this context, began to look less like the Sun misbehaving and more like electron neutrinos changing into muon and tau neutrinos on their way to us. But to confirm that picture, another kind of experiment was needed. In Canada, at a facility near Sudbury, the Sudbury Neutrino Observatory was built with a different strategy. Instead of ordinary water, its large spherical detector was filled with heavy water, in which deuterium nuclei, made of one proton and one neutron, take the place of simple hydrogen nuclei. Solar neutrinos could interact with this heavy water in more than one way. In one reaction, an electron neutrino could convert a deuteron into two protons and an electron. This charged current process was sensitive specifically to electron flavor. In another reaction, any flavor of neutrino could break the deuteron apart into a proton and a neutron without producing a charged lepton, a neutral current process. By measuring both types of interactions, researchers could determine not only how many electron neutrinos were arriving, but also the total number of neutrinos of all flavors combined. When the results came in, they told a very clean story. The number of electron neutrinos detected was indeed lower than what solar models predicted, but the total number of neutrinos of all flavors agreed well with the models. The Sun was producing neutrinos as expected. They were simply not staying in the electron flavor by the time they reached Earth. Some had oscillated into muon and tau neutrinos, which detectors like the home state chlorine tank could not see. Together, the atmospheric results from Super Kamiokande and the solar results from Sudbury and other experiments painted a consistent picture. Neutrinos do not respect flavor as a fixed identity. They oscillate. To oscillate, they must have mass. To have mass, they must interact with something like the Higgs field or with a new field in a way that the original Standard Model did not include. This is more than a technical modification. The Standard Model's treatment of neutrinos as massless was tied to certain assumptions about the structure of the theory. Giving neutrinos mass forces us to extend that structure. There are at least two broad ways to do so. One is to add right-handed neutrino partners and let neutrinos acquire masses through the same kind of mechanism that gives mass to other fermions. Another is to consider the possibility that neutrinos are Majorana particles, meaning that the neutrino and antineutrino are, in a sense, the same entity, with mass arising from a different kind of term in the equations. Each option carries its own implications for how lepton number is conserved or violated, for how heavy unseen neutrino states might exist, and for how leptogenesis could work in the early universe. The details are still being worked out. Experiments searching for rare processes such as neutrinoless double beta decay, where two neutrons in a nucleus transform into two protons and two electrons without emitting neutrinos, aim to probe whether neutrinos are their own antiparticles. Other experiments measure oscillation parameters ever more precisely, trying to pin down the mixing angles and mass-squared differences. From the perspective of the story we are following, the important point is that neutrinos forced the Standard Model to admit that it was incomplete. They did so not with dramatic new forces, but with a subtle pattern of absence and reappearance. A detector would see fewer muon neutrinos from below than from above. A tank of cleaning fluid would catch fewer electron neutrinos than predicted. Only when multiple experiments, with different techniques and sensitivities, were brought together did the underlying oscillation pattern reveal itself. There is a thematic echo here. Earlier, the universe broke symmetries we thought it should keep, introducing tiny asymmetries in weak interactions. Now, neutrinos break a different expectation, that massless particles which carry no electric charge can be set aside as simple. Instead, they turn out to be shapeshifters, actors changing masks as they traverse space, their very existence pointing beyond the neat lines of our established theory. Neutrino oscillations also intertwine space, time, and identity in a way that is quietly unsettling. A neutrino created in a specific flavor state has no single, permanent label. Its identity is a function of distance traveled and energy. Two neutrinos born in the same process can arrive elsewhere, carrying different flavor tags, not because something external acted differently on them, but because of the internal phase evolution of their mass components. Even at the fundamental level, the universe resists giving you fixed categories. From a cosmological perspective, the existence of neutrino mass affects how the universe grows. Relic neutrinos, though extremely light, contribute to the total matter content. Because they move at high speeds for much of cosmic history, they tend to smooth out small-scale structure, suppressing the formation of very small clumps of matter. Precise measurements of the distribution of galaxies and of the cosmic microwave background already place limits on the sum of neutrino masses. The same particles that flicker in and out of flavor in an underground detector also leave fingerprints on the arrangement of galaxies across billions of light-years. In the context of our central question about imbalance, neutrino oscillations do something more conceptual. They replace the idea of disappearance with transformation. Where we once thought neutrinos were simply missing, we now understand that they had changed form. The deficit in one channel is balanced by an excess in another. What looked like absence was, in fact, a failure of our instruments and theories to track identity across space. That shift in viewpoint matters when we later return to the earliest eras of the universe. If neutrinos can oscillate now, they could oscillate then. If their masses and mixings encode physics beyond the Standard Model, then the way they behaved in the first seconds could have helped to create the matter-antimatter asymmetry we see today. Oscillation, in that sense, is not just a curiosity. It is a mechanism by which early imbalances could be stored and propagated. You could say that neutrinos, by breaking the Standard Model, also broke a certain human expectation, that the smallest constituents of reality obey clean, rigid rules. Instead, they show us that even at that scale, subtlety reigns. Identity is not static. Symmetry is not absolute. Mass is not a trivial add-on but a gateway to new physics. And those quiet particles that pass through your body by the trillions, unnoticed, are constantly switching roles, carrying with them the possibility that the universe's first fracture in symmetry was written not in grand gestures, but in the fine print of how they chose, or were compelled, to change. Somewhere between a particle changing masks and a universe choosing sides, the two stories begin to overlap. One way of telling that overlap has a name. People call it leptogenesis. It sounds technical, and it is. But underneath the jargon is a very simple suggestion. The idea is that the first real imbalance in the universe did not start with protons and neutrons at all. It started with the lighter family of particles, the leptons, and especially with neutrinos. Roll the clock back to the first fractions of a second. Temperatures are so high that talking about solid objects or even atoms makes no sense. The universe is a dense bath of quarks, leptons, gauge bosons, and whatever heavier fields were still active at that scale. Almost everything that can be produced is produced. Almost everything that can collide collides. In many versions of leptogenesis, there is an extra cast of characters present at that time. Heavy neutrinos. They do not show up in the Standard Model's original list. They do not exist in our laboratories today, at least not in a way we have managed to see, but they fit naturally into extended versions of the theory that also explain why the neutrinos we do see are so light. The rough picture goes like this. Alongside the three familiar light neutrinos, there exist right-handed partners with very large masses. These heavy states mix with the light ones through what people call a seesaw mechanism. The heavier they are, the lighter the ordinary neutrinos become. You can think of a balance beam with weights at both ends. Push one end up, the other goes down. In the early universe, when energies were enormous, those heavy neutrinos could be created in significant numbers. They would not live long. They would decay into combinations of lighter leptons and Higgs bosons, or their antiparticle counterparts. If the laws of physics were perfectly symmetric, the decays would produce equal amounts of matter and antimatter on average. But if there is CP violation in the neutrino sector, the decay probabilities can favor leptons slightly over antileptons. That slight slant is the heart of the hypothesis. Each heavy neutrino decay is like a coin toss that is almost fair, but not quite. Over many decays, the small bias accumulates into a net lepton number in the plasma. More leptons than antileptons by a tiny but non-zero fraction. At the same time, the universe is expanding and cooling. Conditions are changing fast. Processes that could restore balance by turning lepton number back into radiation may no longer keep up. The system falls out of equilibrium with a built-in surplus. On its own, that surplus would only give you an excess of leptons. Protons and neutrons are baryons. They carry a different kind of quantum number. To turn lepton asymmetry into baryon asymmetry, you need a bridge. In the Standard Model, there is such a bridge in the form of non-perturbative processes called sphalerons. They are rare under ordinary conditions, but in the hot early universe they can be active. Crucially, they violate baryon number and lepton number separately, while preserving a combination of the two. That means that if you start with a plasma in which there are more leptons than antileptons, sphaleron transitions will, in effect, shuffle some of that excess into the baryon sector. After the dust of these processes settles, what remains is a universe with more baryons than antibaryons, more matter than antimatter. The details involve coupled differential equations and thermal rates. The narrative is that an initial asymmetry in neutrino-related decays gets converted into the imbalance that underlies every atom around you. If this story, or something like it, is right, then neutrinos are not just messengers from the first imbalance. They are its origin. Heavy neutrinos would have played their role early, then disappeared from the accessible spectrum, leaving behind their lighter descendants and the macroscopic trace of their bias. There is a certain elegance in this cascade. The same mechanism that gives neutrinos their tiny masses also sets up the conditions for leptogenesis. Explain one oddity. You may explain two. But elegance is not the same as truth. There is a lot we do not know. For one thing, we have never seen a heavy neutrino of the kind these scenarios rely on. Their masses could be far beyond what even our most powerful colliders can reach. They might also sit at lower scales, in which case future experiments might have a chance. For now, they are theoretical actors, motivated by consistency and by a desire to connect dots, not by direct observation. For another, the amount of CP violation in the neutrino sector is not yet pinned down. Oscillation experiments measure differences in the squared masses and mixing angles. They can also probe a phase that, if non-zero, would mean neutrinos and antineutrinos oscillate differently. There have been hints that this phase might be large. There is not yet a firm consensus. And even once it is measured, relating that low-energy phase to the high-energy CP violation relevant for heavy neutrino decays is not straightforward. Different models connect them in different ways. So the big hypothesis is really a family of possibilities. In some, heavy neutrinos decay at temperatures well above the electroweak scale, and the resulting asymmetry is processed by sphalerons before they freeze out. In others, there are resonant effects that enhance asymmetry when masses of heavy neutrinos are close to each other. In still others, the heavy states may live long enough to leave imprints in later cosmology. Each variation reshuffles the details while preserving the core idea. Neutrino physics, lepton number, and CP violation intertwine to produce the 1 in a billion excess we need. Where does the cosmic neutrino background fit into this? It is not a direct recording of heavy neutrino decays. Those happened at earlier times and higher energies. But the relic neutrinos we hope to detect today carry information about how many light species were present, how they were distributed, and how they contributed to the energy density at early times. All of that constrains the space of viable leptogenesis models. If we ever manage to measure properties of the relic neutrino background directly, such as its exact temperature, momentum distribution, and any tiny deviations from ideal expectations, those measurements will act as cross-checks on our theories of the first seconds. Closer to home, experiments that probe the absolute mass scale of neutrinos are quietly tightening the net. Oscillations tell us differences between squared masses, not their overall size. To know how heavy neutrinos are, in an absolute sense, you need other approaches. One method is to look at beta decay very carefully. Tritium, a radioactive isotope of hydrogen, decays by emitting an electron and an antineutrino. The shape of the electron energy spectrum near its maximum depends sensitively on the neutrino mass. If neutrinos were massless, the spectrum would have a sharp endpoint. With a non-zero mass, the endpoint shifts and the shape near that edge changes slightly. Experiments such as the one using a large electrostatic spectrometer in Germany are designed to measure this region with extreme precision. They count electrons, track their energies, and slowly squeeze the upper bound on the effective electron-neutrino mass. The target numbers here are tiny, in the range of fractions of an electron volt. It is like trying to detect a small dent in a smooth curve using a ruler with almost absurdly fine markings. Each improvement in sensitivity rules out whole swaths of theoretical parameter space. Some versions of the seesaw mechanism predict neutrino masses within certain ranges. If the experiments push the allowed window below those ranges, those specific versions become less plausible. A different, even more ambitious method aims directly at the relic neutrino background. The idea is that a neutrino from that background could be captured by tritium, turning it into helium and emitting an electron without an antineutrino in the final state. Because there is no neutrino to carry away energy, the electron would have a slightly higher energy than those produced in ordinary beta decay. If you have enough tritium, and a spectrometer sensitive enough to resolve that tiny difference, you might see a small cluster of events just above the usual endpoint. Those events would be direct evidence of relic neutrino capture. The expected rate is painfully low. With a source mass on the order of hundreds of grams, you might hope for a handful of such captures per year. That sounds discouraging, but numbers can be misleading. It only took a few dozen neutrino events from a supernova to confirm the basic picture of core collapse. It took a small pattern of temperature fluctuations in the cosmic microwave background to revolutionize cosmology. In the same way, a modest collection of relic neutrino captures would punch far above its weight in terms of what it tells us. Experiments along these lines are as much engineering projects as they are physics ones. They demand ultra-high vacuum systems, cryogenic temperatures, intricate radio frequency traps, and an obsessive attention to every possible source of background. Much of the work goes into making the world quiet enough that the soft whisper of a relic neutrino can be heard at all. In parallel, other experiments search for neutrinoless double beta decay, a process that would only occur if neutrinos are Majorana particles. Observing such a decay would tell us that neutrinos and antineutrinos are, in some deep sense, the same state. That, in turn, would influence how we build models of heavy neutrinos in the early universe, and how lepton number violation could have contributed to baryogenesis. Even a null result, if the sensitivity is pushed far enough, would narrow the range of viable seesaw scenarios. All of this might sound like a tangle of technical details, but underneath is a simple question with a very personal shadow. Why is there something here for you to observe at all? The leptogenesis hypothesis answers it by pointing to neutrinos and saying, quietly, that the first meaningful choice the universe made may have been a statistical one, encoded in the decays of particles that do not exist anymore. If neutrino masses, mixings, and CP phases line up just right, they will form a consistent pattern that points back to such an origin. The measured sum of neutrino masses from beta decay experiments, the hierarchy between mass states inferred from oscillations, the presence or absence of neutrinoless double beta decay, the properties of the cosmic neutrino background, the detailed shape of the cosmic microwave background power spectrum. Together, these will either trace a path that matches the leptogenesis picture, or they will force us to look elsewhere. There is a quiet honesty in the way physics handles this. No one can go back and watch the first second play out. All we can do is compare stories. We write down a script for the early universe. We let it run forward in equations. We see what kind of neutrinos, what kind of structures, what kind of asymmetries it produces. Then we check whether those match what we see in experiments and observations now. In that sense, the big hypothesis is not a definitive claim. It is an invitation to test whether the lightest, least interactive particles we know are secretly custodians of the universe's earliest unfairness. If they are, then every neutrino streaming through you carries, in its mass and its flavor and its ghost-like indifference, a record of the moment when perfect balance was quietly abandoned in favor of a world where something, rather than nothing, could persist. The same particles that may have carried the universe's first imbalance have not gone quiet. They still pass through you, through the planet. And some of them now leave faint marks in machines we have lowered into ice, rock, and water, like eyes opened in the dark. One of those eyes sits at the bottom of the world. In Antarctica, engineers and physicists have turned a piece of the ice sheet into a telescope that does not look up, but inward. They drilled holes about 2.5 kilometers deep into clear glacial ice and lowered strings of light sensors, hundreds of meters long, until a cubic kilometer of ice was threaded with more than 5,000 small, glass-enclosed detectors. Once frozen in place, those sensors wait for the briefest flashes of blue light. The principle is the same as in the mines and water tanks we have already visited. When a high-energy neutrino happens, very rarely, to strike an atomic nucleus in the ice, the collision produces charged particles that move faster than light can travel in that medium. They generate a cone of Cherenkov light, a sort of optical shock wave. The sensors register that light. By comparing arrival times and intensities across the array, computers reconstruct the direction and energy of the original neutrino. Most of what IceCube sees are atmospheric neutrinos and muons from cosmic ray showers. But every so often it records an event with an energy far beyond what those local sources can easily supply. These are candidate neutrinos that have traveled from distant galaxies, carrying information about black holes, jets, or other violent astrophysical processes. When enough of these events are collected, patterns emerge. One particularly famous case linked a single very high-energy neutrino to a flaring active galaxy, a blazar, whose jet happened to be pointed near our line of sight. Light telescopes and gamma-ray observatories saw the flare. IceCube saw the neutrino. Together, they traced a path from a small, bright knot in the sky back to the heart of a galaxy. Scenes like that are the beginning of neutrino astronomy as a routine practice. Instead of thinking of neutrinos as rare, exotic guests, experiments like IceCube invite us to treat them as another constant stream of information, a high-energy channel running in parallel with the photons we have always used. Other detectors play different roles. In Japan, the Super Kamiokande water tank continues to watch for atmospheric neutrinos, solar neutrinos, and the ghostly first signs of a nearby supernova. It sits under a mountain, filled with tens of thousands of tons of ultra-pure water. The walls covered with enormous light sensors. A nearby supernova in our own galaxy would send a burst of thousands or tens of thousands of neutrinos through it in a matter of seconds. Long before the exploding star brightened in optical light, that burst would set off alarms in control rooms. There is a network for such alarms, a quiet agreement among neutrino experiments spread across the planet. If several detectors see a sudden spike in neutrino events within a short interval, automated systems can send out an alert to observatories worldwide. Telescopes can then pivot toward the likely region of the sky, ready to catch the rising light. Neutrinos become the early warning system for stellar death, a private message that lets us prepare for a public display. In the coming years, a new generation of detectors aims not only to listen passively, but also to probe actively how neutrinos behave over known distances. One of the most ambitious efforts is being assembled under the name Deep Underground Neutrino Experiment. The idea is to build massive detectors filled with liquefied argon deep in an old mine in South Dakota, while a powerful accelerator near Chicago produces beams of neutrinos aimed straight through the Earth toward them. The distance between source and detector will be about 1,300 kilometers. Along that underground path, neutrinos will oscillate between flavors. By comparing how a beam of neutrinos changes with how a beam of antineutrinos changes, Dune and similar experiments hope to measure any difference between their behaviors. That difference, if it exists and is large enough, would be another expression of CP violation. This time, in the lepton sector. It would be a piece of evidence in favor of the idea that neutrinos help generate the universe's matter-antimatter asymmetry. The detectors themselves are designed almost as instruments for listening. A neutrino interaction in liquid argon produces a spray of charged particles. As those particles drift in an electric field, they induce signals in layers of fine wires. By reading out those signals over time, the detector reconstructs a three-dimensional image of the event, a kind of bubble chamber in digital form. Each recorded interaction is a frozen moment in a long beam, a single word in a long sentence about how neutrinos change as they travel, gathered together. All these devices, ice cube in the ice, super Kamiokande in rock, Dune's future tanks of argon, other experiments in Europe and the Americas, form something like a loose sensory organ for the planet. They do not share a single brain. They are funded and operated by different groups, with different priorities. But taken as a whole, they give Earth a way to respond when neutrinos arrive. They are today's neutrino eyes on the universe. The work they do is not always glamorous. Most of the time, they record background. Atmospheric neutrinos, radioactive decays, occasional instrumental noise. Teams spend years refining calibrations, checking cables, correcting for temperature drifts, rebuilding failed sensors. For every event that makes the news, there are countless others that simply add to the baseline understanding of how the detector behaves. Every so often, though, these eyes catch something that challenges our confidence. In the early years of the last decade, an experiment named Opera, which was designed to observe neutrino oscillations by sending a beam from CERN in Switzerland to a detector in Italy, reported a startling result. Their measurements seemed to show neutrinos arriving about 60 nanoseconds earlier than light would have over the same distance of roughly 730 kilometers. If true, that would have meant neutrinos were traveling faster than light, breaking a central pillar of relativity. For a brief period, the results sent ripples through both the scientific community and the wider culture. Some were eager to declare that Einstein had been overthrown. Others were cautiously skeptical. Many experiments and theorists rushed to examine possible explanations, from mundane timing errors to exotic new physics. The collaboration itself, to its credit, presented the result as puzzling and provisional, and invited scrutiny. Over the following months, careful checks uncovered problems. A loose fiber optic cable, a fault in the master clock used for timing. Once these were corrected, the apparent superluminal signal disappeared. Measurements fell back in line with the speed of light limit. Neutrinos, it turned out, were not breaking relativity. They had exposed, instead, how sensitive these experiments are to small systematic errors. The episode ended with resignations and retractions, but also with a hard-won lesson in restraint. That lesson fits the tone of neutrino physics as a whole. These particles have a habit of sitting at the edge of what we can reliably measure. They demand instrumentation that pushes timing, energy resolution, and background rejection to extremes. Sometimes, when something unexpected appears, the first task is to check whether the universe has revealed a hidden rule or whether a cable has simply been left a little loose. Despite setbacks, the overall arc is one of gradually increasing clarity. High-energy neutrino observatories tie individual neutrinos to specific astrophysical sources. Long baseline experiments map out oscillation parameters and seek CP violation. Reactor experiments look for subtle disappearance patterns at short distances. Solar neutrino detectors continue to refine our picture of what happens in the sun's core. Each of these is a different way of asking neutrinos what they remember. From a narrative point of view, there is a quiet symmetry in how we now use these particles. At the largest scales, neutrinos help us probe black holes, exploding stars, and the first instance after the Big Bang. At the smallest scales, they let us test the structure of the standard model, search for new symmetries or their breaking, and constrain the masses and mixing angles that define their own identities. Between those two extremes lies the human scale, where neutrinos are tools in medical imaging, in monitoring nuclear reactors, in probing the interior of the Earth through geoneutrinos emitted by radioactive decays in the mantle and crust. If you step back, you can think of all current neutrino experiments as a kind of rehearsal. We are learning how to listen, how to disentangle background from signal, how to coordinate across continents when a burst arrives. We are training our eyes so that when the universe offers a clearer view of its early decisions, perhaps through direct detection of the relic neutrino background, perhaps through a nearby supernova, perhaps through a precise measurement of leptonic CP violation, we will be able to recognize what we are seeing. Meanwhile, neutrinos keep passing through us, indifferent to whether we are paying attention. The detectors we have built are, in the end, small perturbations in their path, slight chances for them to leave a mark. Most do not. Most continue on, carrying their part of the universe's history into the future without ever being recorded. There is something grounding in that. Our experiments, for all their complexity, do not control the story. They only sample it. Each Cherenkov ring in a water tank, each streak of blue light in Antarctic ice, each faint signal in argon, is a single frame pulled from an endless film. And behind those frames is the same underlying narrative. A universe that, very early on, let imbalance in, and now keeps sending out particles that remember, in their properties, and their silence, how that choice was made. The particles that slipped through the first second without leaving a visible trace are still moving, still carrying whatever bias they were given. The question now is not whether they remember, but how far we are willing to go to learn to read what they remember. If you look at what physicists are trying to build over the coming decades, you can see an outline of that ambition. It is not a single machine. It is more like an ecosystem of devices, each one tuned to a different part of the neutrino story. Together, they aim to turn a scattered collection of clues into something closer to a logbook. On one side, there are the experiments that watch beta decay with almost obsessive attention to detail. A speck of tritium, barely enough to weigh in your hand, becomes a laboratory for measuring how much energy an electron carries away when a nucleus decays. Near the very end of the energy spectrum, in a narrow region where counts are rare, the exact shape of the curve depends on the neutrino mass. By slowly tightening the uncertainty there, these experiments are trying to pin down the absolute mass scale of at least one neutrino flavor, down to fractions of an electron volt. It sounds abstract, but each small reduction in the allowed mass range crosses out entire branches of theoretical possibilities. Certain versions of the seesaw mechanism require neutrinos to be heavier than a given threshold. If measurements show that they are lighter than that, those versions quietly leave the stage. The logbook gains a note. The universe did not choose this path. On another side, there are the plans to listen for the relic neutrino background directly. The idea is still closer to a sketch than to an everyday instrument. But the principle is clear. Use a large, carefully structured target of tritium. Wait for neutrinos that have been drifting since the first second of cosmic history to be captured by those nuclei. Look for electrons whose energies sit just above the usual endpoint of beta decay, like faint marks at the edge of a page. The capture rate is expected to be painfully low, perhaps a few events per year in a generous design. But each event would be a direct interaction with a neutrino, born when the universe was barely out of its initial plasma. It will not feel dramatic if it works. There will be no photograph to share, no obvious picture of a baby universe. There will be tables of numbers and error bars, a small excess of counts in a particular energy bin, debated and checked and rechecked. Underneath that, though, would be something quiet and profound. A direct line from a detector on Earth to a population of particles that have been free streaming since the earliest time we can hope to access. Between these extremes sit the oscillation and CP violation experiments. Long baseline beams shot through the crust, measured by huge detectors buried under mountains or in mines. Reactor neutrino experiments at carefully chosen distances, watching for patterns in disappearance and reappearance. Atmospheric and solar neutrino measurements, refining mixing angles and mass differences. From one angle, these are just parameter hunts. They measure 3 mixing angles, a handful of mass splittings, perhaps 1 or more CP violating phases. But those numbers are not arbitrary. They encode how strongly different flavors mix, how different mass states separate over time, whether neutrinos and antineutrinos really change identity in the same way. Once fixed, they become constraints on any model of leptogenesis. Certain patterns of mixing and mass cannot support a large enough early asymmetry. Others can. In that sense, every digit in a mixing matrix is a sentence in the neutrino logbook. The future also holds more sensitive searches for neutrinoless double beta decay. If 2 neutrons in a nucleus can transform into 2 protons and 2 electrons with no neutrinos emitted, it would mean that neutrinos are their own antiparticles. That single fact would reshape how we think about lepton number, heavy neutrinos, and the mechanisms available for producing a lepton asymmetry in the first place. A clear detection would be like finding a long suspected entry in the logbook, written in a language we had only partially guessed. Set against these concrete efforts are 2 broad possibilities. In one, all of these measurements gradually converge on a picture in which neutrinos are exactly the kind of agents leptogenesis needs. Their masses, mixing angles, and CP phases line up in a way that allows heavy ancestors in the early universe to decay with just the right bias. The relic neutrino background, if we detect it, matches a thermal distribution with tiny deviations that fit those same parameters. The cosmic microwave background and large-scale structure measurements confirm that the number of neutrino species and their total mass all fit into a single, consistent story. In that scenario, the logbook reads clearly: neutrinos are not only messengers, they are the original scribes of imbalance. The slight preference they embodied in their earliest decays, amplified by the dynamics of an expanding, cooling plasma, becomes the 1 in a billion excess of matter over antimatter. The existence of every atom in your body is tied in a calculable way to a bias in processes that played out within the first second. In the other possibility, the numbers do not cooperate. Neutrino masses might turn out to be too small or arranged in a hierarchy that does not favor efficient leptogenesis. CP violation in their oscillations might be present but weak, or even effectively zero. Neutrinoless double beta decay might stubbornly refuse to appear, even when experiments reach sensitivities that rule out most Majorana scenarios. The relic neutrino background, once probed, might look exactly like the simplest model with no hints of extra species or unusual behavior. If that happens, neutrinos do not leave the story. They remain crucial components of the cosmic energy budget and key actors in supernovae, structure formation, and thermal history. But they may not carry the responsibility for the first imbalance, The logbook would, in effect, tell us that we have been looking in the wrong column. Somewhere else, in physics we have not yet uncovered, the universe would have chosen its asymmetry. Both outcomes are unsettling in their own ways. The first ties our existence very tightly to a specific microscopic mechanism. The second leaves us with a larger blind spot, a reminder that the most important decision in the universe's past might be encoded in degrees of freedom we have not even written down yet. Either way, the experiments we are building now will narrow the space of possibilities. They will act less like searchlights and more like careful editors, crossing out lines that reality does not follow. There is another layer to all of this that is not about the particles or the equations, but about how we tell our own story against that backdrop. We are used to thinking of balance as an ideal. In personal life, in society, in ethics, symmetry and fairness often stand as goals. There is a quiet temptation to project that preference backward, to imagine the early universe as a harmonious state that later became fractured and flawed. In that picture, asymmetries feel like damage. What the neutrino logbook suggests is almost the reverse. At the fundamental level, a perfectly symmetric universe would have erased itself. If matter and antimatter had been produced and destroyed in exact pairs, if CP symmetry had held without exception, if every process had a mirror twin with perfectly matched probability, there would be no structure, no chemistry, no observers. Balance, in that sense, is the path to emptiness. The universe we inhabit is built on a small failure of that balance, a bias in decay probabilities, a slight skew in how particles and antiparticles behaved as the plasma cooled, a set of symmetry breakings that are measurable, repeatable, and, in some cases, encoded in the parameters of neutrino physics. Existence, in this view, is not what happens when the universe stays faithful to its symmetries. It is what happens when it lets itself deviate. Reading the neutrino logbook is, therefore, also a way of rewriting how we relate to absence and disappearance. Where an older picture saw missing neutrinos as losses, as particles that had somehow failed to arrive, oscillation tells us they have changed form. Where an earlier cosmology spoke of annihilation as wholesale erasure, the tiny imbalance that halted complete annihilation becomes the seed of everything. What looks like vanishing is often a transformation we have not yet learned to track. On a more immediate level, this reframes the familiar morning room from the opening, the same sunlight through the window, the same dust in the air, the same quiet sense that everything is, for a brief moment, in order. Underneath that scene, an invisible storm of neutrinos is still passing through you every second, some from the sun's core, some from distant cosmic accelerators, some perhaps from the first seconds after the Big Bang. If the experiments succeed, we will be able to say, not as metaphor but as a careful statement, that a few of those particles have had their properties measured in ways that tie them back to the first imbalance. Their masses will be known within narrow limits. Their mixing patterns will be mapped. Their background distribution will have been sampled. The universe's early confession of unfairness will not be a vague idea but a sequence of numbers written in detector logs. Nothing in your daily life will change when that happens. The world will look the same cities, the same routines, the same quiet rooms lit by an ordinary star. But the story you can tell yourself about why any of that exists will have shifted. Instead of picturing a lost original harmony, broken by later imperfections, you will know that the origin was already tilted. The first state was not a perfect song, but a slightly biased process. The fact that you are here to ask about it is evidence that the bias was real. That knowledge is not a cure for anything. It does not resolve personal grief or social conflict. It does not offer comfort in a simple way. What it does offer is a different kind of grounding. It says that asymmetry is not a blemish on an otherwise pure reality. It is the condition for reality to have structure at all. The neutrinos that pass through you, mostly unnoticed, are among the last remaining links to the moment when that condition was established. So you sit again in that room. Sunlight on the floor. Dust moving in slow patterns. Somewhere deep under ice, under mountains, in carefully cooled halls, machines are listening for particles that do not want to be heard. Each time a neutrino leaves a trace, a line is added to a logbook that began long before any observer existed. As we learn to read that log, we are not just doing better physics, we are quietly replacing one image of the universe with another. Not a story that begins in perfect symmetry and falls, but a story that begins in imbalance, and from that fracture allows everything else to unfold.